So hello everybody, my name is Lukas. I'm the product owner of the container platform of Swiss Federal Railways, and that's Michael, one of my engineers. So let's get started. Swiss Federal Railways. We have about 34,000 employees working in IT, about 1,500 and 700 developers, which are the customers of our container platform. About 11,000 trains on the network per day and about 1.1 million passengers daily. And the mobile application is one of our biggest internal customers, which has about 3.5 million active users daily, and that's about 40% of the Swiss population. And we also sell about 300,000 tickets per day over this application. A few fun facts. We also operate the longest tunnel with 57.1 kilometers, and we also have 8 hydroelectric power plants. And many people confuse Switzerland with Sweden, but we are the land of chocolate and Sweden is the land of moose. So, let's do a short chocolate quiz. What's the customer punctuality of our trains? That means the train arrives within less than 3 minutes of delay. So is it 72.1, 79.4, 88.3, or 92.5? Yes? Can't hear you. 4, okay. Good, you get some chocolate. Be careful. A few more. And the last one. Okay. Well, so our container platform. We started in 2015 with OpenShift 3.0. Yes, 0. We had one cluster on AWS and one huge cluster, at least for that time, on-prem. And yes, operation was not as good as today, I have to say. Our monitoring missed the expiration of internal CA certificate, which got us into the news. We had long nights because of Ansible gather facts during cluster updates. And then you realize you have to do it again. All different kinds of performance issues with SDN, IP tables, the number of pods on the nodes, etc. So the number of clusters grow over time, especially with OpenShift 4. And today we have 42 clusters, about 800 nodes with 11,000 CPUs and tons of memory. And the distribution is like this: 6 development, 19 test, and 17 production clusters. And we run a multi-cloud strategy. We are on AWS, on Azure, and on the Open Telecom Cloud. And if you have never heard from the last one, you can feel yourself lucky. Okay, the application stack is mostly Spring Boot. And we have Kafka and PostgreSQL. So you see here the container platform team in front of one of our rescues and firefighting trains. We are 7 engineers, including me as product owner. We also have a Scrum Master, and we do 7/24 on-call service and also have an engineer on duty during business hours. And we have a lot of fun at work and beside work, as you can see here. On the left-hand side, we do some mountaineering. On the right-hand side, we bake our own cookies. So let's hand over to Michael.
Thank you, Luke. As you have just heard, we are currently managing 42 OpenShift clusters on 3 different clouds, and we expect the number of clusters to go up. And over the next few slides, I would like to show you how we one core concept of how we manage these different clusters. And to get started, let's quickly talk about pets and cattle. I have no idea if you have heard of the terms, so just a quick introduction. Pet infrastructure refers to infrastructure that is dealing with individually customized, named clusters, servers, whatever. And cattle-style infrastructure is infrastructure dealing with infrastructure at scale. So the individual server or object doesn't matter. It can be tens, hundreds, thousands. And as an engineer, I prefer cattle-style infrastructure because, well, it's all the same. If I have to change something, if I have to update something, I only have to test it once, and then I can apply it to the infrastructure, and because everything is the same, well, it works the same everywhere. So let's check our infrastructure if it is actually pets or cattle. So it's all OpenShift clusters. It's cattle, right? Well, not so much. We already have to differentiate between so-called dedicated and shared clusters. Shared clusters are clusters that can be used by any project, any IT user in the company. They can just get a namespace, a project on the cluster, and work with it. And dedicated clusters are specific clusters installed for certain projects that have, well, larger requirements. But again, it's just two types. It can still be cattle, two different types of cattle. But again, reality is harsh, and we are not only dealing with these two types of clusters, we have far more categories to deal with. For example, different stages, different clouds, and they all come with their own specific requirements and settings. And so we have to accept this truth. We are not a cattle farm, we are a pet hotel. And I would like to show how we tame our pets, how we set them on a leash to provide the services we do. So let's start by having a look at the tools we are using. It's actually quite short list, but it's quite powerful list. So we are working with a central mono Git repo that contains all our platform infrastructure code. This code is mainly Helm charts, and they are different value files. And these Helm charts and value files are then deployed via Argo CD, controlled with its GitOps operator brain you can see here. Okay, so how does such an application, such an installation look like? At its center, you have an Argo CD application that actually specifies which Helm chart gets deployed to which cluster with which values. And in this example, for our cluster A and a single application, it's quite easy. You have your Helm chart, it has its own central common values file, and then you have a cluster-specific value file that contains, well, whatever you need for the cluster. For example, if this is an AWS cluster, the cluster value file contains everything that's relevant for the cluster itself and the specifics for AWS. So let's add a second cluster that also contains an application referencing the same Helm chart. Let's say it's the Helm chart for storage classes. Again, it has its central values file that's the same for all clusters, and it has its specific values file that contains everything specific for this cloud and this cluster. That's still easy. Now at a third cluster, also on Azure. With the same system, you also have the central values file and the cluster-specific value file. But now you have a problem, because everything that's specific for Azure, you would need to duplicate between the value files of cluster B and C. And you might argue, well, let's add another value file specific for Azure. But that doesn't scale, because as I have shown you, we have multiple categories. Not only AWS and Azure, we have different stages and so on. And it doesn't end there. We also have the same problem regarding which application gets deployed where. So we already talked about the application based on chart X or storage classes. But then you have applications that maybe are only specific to clusters running on AWS or applications running on clusters on Azure. To give you a number regarding this complexity, we are dealing with 1,600 applications currently just to manage the control plane of our 42 clusters. Just imagine how many value files we are dealing with. So, wouldn't it be nice if we can handle it differently? Example like this. It would be very nice if we could just say, well, we have groups that we can assign to our clusters, and these groups cover what applications are deployed on the cluster and what value files are assigned to these applications. And for everyone who knows, Argo CD knows, well, Argo CD has no concept of groups. So we need something that actually implements this and uses the groups to actually render our applications, and in the end gets us from here to there. So let's have a look at how we do that. We started at the file system. I mean, we are dealing with charts that are in our monorepo, and we are dealing with value files. So we have in our monorepo a directory containing our charts, one directory per chart with their specific value files. We also have a directory for values, specifically our cluster-specific values, one directory per cluster, and one YAML file, one value file per cluster. That's actually the structure I've shown you initially, where each application has one value file, and each cluster also has a cluster-specific one. So let's add groups. And what we did here is we said, well, instead of defining some artificial groups, let's map our grouping concept to the file system itself. So in this case, we have 4 groups. One stage test for everything located in the stage test directory, and then stage prod, cloud Azure, cloud AWS. And this is just an example. It can be extended however you want, either in the breadth or in the lower levels. So let's have again a look at our big picture. We now have groups for our value files. By just placing them in the correct folder, we have assigned a value file for an application to a group. So to have a quick look at a single file here, so instead of calling it, well, Cloud AWS app y values, let's split this up and place it in the correct folder. So Cloud the AWS folder and then app y for the application. And now the application app y gets this value file assigned if a cluster has this cloud. So we have defined a way to place files in folders. Yay. Well, that's not actually the interesting part. What we also do is we have to map applications to our groups. And for that, we use the apps of apps pattern. This is, we have an Argo CD application, a Helm chart, that renders all the other applications. And this Helm chart actually is responsible for the mapping of everything to the cluster. So we have one value file that specifies what application belongs to which group. So let's have a look at a single entry here. This value file defines for each group which applications go where. So in this case, you see we have the Cloud Azure group, and in this group, the applications AppU and AppV are assigned to this group, and they are deployed to the AppU namespace and AppV namespace. So every cluster that has this group assigned gets these applications deployed. We also have a way to exclude applications. That becomes relevant if you have multiple groups assigned to a cluster. You might encounter situations where you need to take out a group that was introduced by another group. Hopefully you don't need it, but given enough complexity, you might encounter it, so it is nice to have it. So let's tie everything together, because what I haven't shown you yet is how clusters get their groups assigned. And that's what the clusters YAML file is for. So this is a single entry for cluster C. It defines the basics, the name of the cluster, and the API endpoint as needed by Argo CD. It then defines a list of groups for the cluster, in this case, Stage Prod and Cloud Azure. So this would get all the applications deployed in these two groups. As I have shown in Cloud Azure, there is the app U and app V. And what you can also do, you can assign individual applications to the cluster, should the need arise. For example, if you have a development cluster and you want to test a new application, instead of assigning it to a group, initially you can just say, well, this cluster gets this application. And again, you can exclude applications introduced by groups. And to give you a more realistic view on this, this is actually the list of groups we have assigned to one of our clusters. So yeah, as you see, we do have to deal with a lot of groups here. But as I said initially, we are dealing with 1,600 applications, around 35 applications per cluster on average. And this concept brought us down to around 8 groups per cluster on average. So reducing the complexity of each cluster definition to around 1/4. So let's have a view back on our big picture. So now we have a way to define a group, assign it applications, and assign values to these applications. So depending on what group a cluster has, it gets the proper settings and apps deployed. And in the end, the app of apps pattern ensures that the different application resources are rendered. Aside from this, there is more to our infrastructure that we do. So we have a concept of delegating cluster admin to our users without having them to be full cluster admin. We have common values, for example, if you need some values, for example, the cluster name in multiple applications. We have secret handling based on Mozilla ZOPs. We have a concept of shared apps that's especially interesting for operator lifecycle managed applications where each operator in and itself more or less has the same resources. We have an automatically generated cluster inventory based on the data in our monorepo. And some convenient thing is we make intensive use of Argo CD application labels. Nevertheless, time flies. And yes, thank you. That's the direction I wanted to have. And I could talk hours about the Helm code actually implementing all of this, but we do not have time for this. And everything I've shown you, the actual implementation with some examples, is available on GitHub, and you can download it there and experiment with it. And but the single thing, and I need to say this, that you cannot download there is actually a team working on these things with you. And I'm very, very proud to work on a team that actually maintains this infrastructure together. And it's really, really fun. And Luke, I have to thank you and everyone else in the team. It's really great fun working with you. And yeah, that's it. Thank you, everyone. Thanks for listening. And goodbye.